Right, so today our topic is going to be one that theoretically should be pretty straightforward, which is free groups. And in this section we're going to take our base ring to be the integers. You might recall the free abelian groups are just the product of a number of copies of the integers. Let X be a set with a free group of Fx. Now we're going to let f to the n of x be the descending central series of fx, defined where the first element is just all of fx, and the nth element in the series is the commutator of fx and f to the n minus 1 x for n greater than 1. The associated graded group is actually a Lie algebra, as we saw in the earlier episode. As the grade of f of x is the sum of all of the graded n of f of x with the nth grade of n of x being the quotient of the nth element in the descending central series of x divided by the following n plus 1 x. We see that the first grade of f of x is f of x modding out the commutator, which, as you know, represents kind of the non-commutativity, is the free abelian group on X. Which, if we recall, is equal to the integers, product of the integers indexed by our set K, X, not K. Right, theorem. The canonical map from X to the first grade of f of x induces an isomorphism of Lie algebras phi1 from the free Lie algebra of x to the graded free group. that comes with a corollary. The groups grn f of x, which is fn of x over f to the n plus 1 of x, are free Z modules and if x is finite with cardinality D, then the rank of grn f of x is just our LD of n. Recall that this LD of n is we saw it before. LD is the rank of the nth component of the free Lie group. And that's pretty clear just from having this isomorphism. Now, it says, we're going to deal with the free associative algebra on X. So, let the nth grade of the free associative algebra of X, the component of degree n of the associative algebra of X, the completion ASX hat of ASX is defined as the infinite product of AS n to the x. And an element f of ASX hat can be represented by a formal series f is the infinite sum from 0 to infinity, as the product was, of fn, with each fn being in ASX to the n. So, define a homomorphism theta from f of x to ASX tilde star, we'll see what that is in a bit, by theta of x equals 1 plus x, where this very confusing ASX tilde star is the multiplicative group of the invertible elements of ASX hat, And obviously 1 plus x is going to be invertible by these typical, 1 minus x plus x squared minus, and so on. Now, for any natural n, so we're not counting 0, define m hat to the n in ASX hat as, well, m hat to the n is equal to the set of f, where f is the sum of these fm in ASX hat as before, with f0 through f to the n minus 1 being 0. So essentially, this m hat to the n is the set of elements in AS hat of x whose smallest non-zero component is of degree n. And then we're going to put fnx tilde equal to the theta inverse of 1 plus m hat to the n. So this is essentially our copy of hfnx tilde prime is essentially our copy of m hat to the n back in our f of x. Then g in f of x is in fxn prime if and only if theta of g is 1 plus the sum for m of at least n, n-let of at most m, cn. Notice that fx1 prime is just all of f of x, and that f to the nx prime is in fxn minus 1 prime. Sorry, things are happening. Give me 1 moment, please. Alright, everything's good. Alright. Now, theorem is that if each fxn prime is just fxm, the nth grade of fx. Now, proof. Now this is going to be a proof for both theorems. It's going to be a proof for this theorem up here that fxn prime is just the nth grade of fx, and also our previous theorem that the canonical map from x to the first grade of the free group of x induces an isomorphism of Lie algebras from the free Lie algebra to the grade of the free group on x. We're going to prove both of those here. So our isomorphism from the free Lie group to the graded algebra of f of x is surjective. We get that for free essentially because there's B. We get that the set of fxn prime is a filtration of fx as, and we get that fx1 prime is equal to fx, so we just need to show that fxm prime and fxp prime are inside fxm plus p prime. Alright, and for that we're going to take g in fxm prime and h in fxp prime, so that by definition theta of g is equal to 1 plus g with g inside of m hat of m, and likewise theta h is going to be 1 plus capital H with h in m hat to the n. P, sorry. Keeps throwing me off. Then we have GH equals HG times the commutator of G and H, and theta of GH should be 1 plus G plus H plus GH, theta of HG 1 plus H plus G plus HG. We also get from the fact that theta is a homomorphism, that theta GH equals theta HG times theta of the commutator of G and H So theta of the commutator of G and H is equal to 1 plus GH minus HG plus some higher terms which are going to disappear out. Therefore, GH is in f the x of m plus p prime, and therefore this whole thing is a filtration. We define a natural map eta from this prime filtration of the graded algebra of fx generated by this prime filtration to the associative algebra on x. How do we define this? We let C be in the nth prime grade of the free algebra on free group on X. Let G be an element of f prime n of x, a representative, and theta G is going to be equal to 1 plus gn plus 1 and so on, with each gp in the pth component of the free associative algebra on X. We then define eta of C as being equal to this Gn. We then get from our theta on the commutator that this is a homomorphism. Then eta is a Lie algebra homomorphism. Now, since that the collection of f, x, and prime is a filtration, we know that our original filtration is like the most specific, so we get that each nth component of fx has to be inside the nth component of of f prime x. It's probably not the best way to say that, but you know what I mean. Which induces a homomorphism of C from the graded free group of X to the prime graded free group of X. Now, we're going to consider, so we have the free Lie algebra, our phi1 sends this to the grade of the grade of the free group, C sends that to the prime grade of the free group, which eta sends to the free associative algebra of X. This map is surjective, and this one is injective. This gives us our map phi from the free Lie algebra to the free associative algebra. I guess this should be a subscript as well. Which is injective. Hence, phi1 has to be injective, and therefore is an isomorphism. Now, let's show that the nth component of f of x is the prime nth component of f of x inductively. The base case, they're both going to be equal by definition, so you can just skip that. Suppose we have this for n minus 1. Then we have that fn of x is in f prime n of x, which is in f prime n minus 1 of x, which is, by the induction hypothesis, just fn minus 1 of x. And the injection of the n minus 1th grade of f of x into its prime version is the canonical map of f to the n minus 1 of x over fn of x to fn minus 1 of x over fn of x prime, which by its injectivity gives us fn of x is equal to f prime n of x. Alright, well, we kind of got to start a new topic. I don't know if we'll get all the way through it, but we'll see how far we can get. New topic here is the Campbell Hausdorff formula. Here in the ground ring K is a Q algebra. Alright. Theorem. let X be a set then the free Lie algebra of X coincides with the primitive elements of the associative map, or the free associative group on X, which we recall is the set of W in the associative algebra of X, where the diagonal map is just equal to W tensor 1 plus 1 tensor W, where, this diagonal is the diagonal map from the free associative algebra to the tensor product of it with itself. Now, since the free associative algebra of X is identified with the universal enveloping algebra of the free Lie algebra of X, we've already shown this. Now, define the completion which is going to be the completion of the free Lie algebra of Lx by Lx hat is equal to the infinite product of ln x. We still have the completion of the free associative algebra. This is the same construction, just for the free Lie algebra. We also define the completed tensor product this is going to be the free associative algebra on X, the completion, the tensor, and the tensor itself is going to be completed. And it's going to be with another copy of the completion of the free associative algebra on X. This is going to be, as you might imagine, the product of the tensor of every possible ASP to the X, tensor ASQ to the X, every possible combination. Then the diagonal map on the free associative algebra X extends to a map delta from the completion of the free associative algebra on X to the completed tensor product. Because normally this would just be like tensor of that with itself. Here this tensor is also completed. And then our theorem persists. So essentially we still have that this theorem that the free Lie algebra of X coincides with the primitive elements of the free associative algebra of X. If we complete all the associative algebras there, we still get that theorem. Okay. Well, maybe we'll just finish off this chapter. We'll see how long it takes. Theorem. We're going to let m hat with no power be not only a subset of the completion of the free associative algebra of X, but be an ideal, namely the ideal generated by our set X. Then we're going to define two maps, the exponential map going from the set M to the set of 1 plus M, and conversely the log from 1 plus M hat into M hat by essentially just their power series, where exp of x is just the sum of x to the n over n factorial, and the logarithm of 1 plus x is the sum from 1 to infinity. I guess this one will be from 0 to infinity of -1 to the n plus 1 times x to the n over n. Now the theorem states that essentially these two functions are inverses in the way that you would hope. It's hard writing the that symbol when the functions are both just words. And log, I forget, why do I not remember what that's called? Composition. Yeah, the composition looks too much like a letter O. And proof. So we're going to show that exp log, so okay, we're going to let y be in m hat. Okay, for an indeterminate, we're going to call t the exponential map of the logarithm of 1 plus t equals 1 plus t holds in Q, the power series ring Q of t. Since y is in m hat, there is a continuous holomorphism f from Q, the power series ring in T on Q, to the free associative, the completion of the free associative algebra on X, as we essentially just turn every copy of our T into Y. And so we can just apply that to our known function that exp log of 1 plus t is 1 plus t, we get our desired theorem. And this theorem has a corollary, of course, that the exponential map defines a bijection of the set of alpha in M hat, where alpha is a primitive, onto the set of beta in 1 plus m with delta of beta equal to beta tensor beta. And how do we know this? Let alpha be in M hat and beta be the exponential map of alpha. I guess we should write it as e to the alpha, which is a bit confusing, but it'll make some notation later on, I think, make a bit more sense. Since our diagonal map commutes with the exponential map, and alpha tensor 1 with 1 tensor alpha, then we get the following calculation that the diagonal map of B is the diagonal map of e to the alpha is equal to e to the diagonal map of alpha, which is e to the alpha tensor 1 plus 1 tensor alpha, which is e to the alpha tensor 1 e to the 1 tensor alpha, which is, we saw by definition, B is e to the alpha, so this is just going to give us beta tensor 1 times 1 tensor beta, which is just beta tensor beta. Now, since I introduced this chapter as being on the Campbell-Hausdorff theorem, we may as well finish off this video with the Campbell-Hausdorff theorem. So, theorem, and this is, of course, Campbell-Hausdorff. So we're going to let X be the set of two distinct elements with X not equal to Y. Then e to the X, e to the Y is equal to e to the Z. For some Z in the completion of the Lie algebra, free Lie algebra of X. And let's take a look at the proof. Since we have e to the X and e to the Y in our 1 plus m, then have that their product is in 1 plus m, since that is unreadable, since the exponential map is a bijection, there exists a unique z in m hat such that e to the z equals e to the xy, e to the x, e to the y. We have, now we don't know this is in Lx hat though yet. We have that diagonal of e to the z is the diagonal of e to the x, e to the y, equals the diagonal of e to the x times the diagonal of e to the y. Oh, that is unreadable. Okay. Which is equal to e to the x tensor e to the x times e to the y tensor e to the y, which is just e to the z tensor e to the z, which by our corollary by our previous results, I guess because we're referencing a couple of the things we've shown here, z is primitive, it's a primitive element, and so z is in the completion of Lx hat, of the free Lie algebra on X. Alright. So, a couple more, one more, just a little more discussion on this topic here. That's the end of this proof. So now we're going to let X be an arbitrary set, and z times the commutator of x and y be the element of the free Lie algebra of the elements x and y, which is inside of the completion of the free Lie algebra of x, such that e to the x, e to the y equals to e to the z times the commutator of x and y for all x and y in X. We have the z times the commutator of x and y is the sum from n equals 1 to infinity of z to the n of x comma y, where z to the n of x comma y is inside L of x to the n. We can calculate the first three homogeneous components of this zx comma y as, well, what are they? They're on another page. z1 of x comma y is just x plus y. z2 of x comma y is half of the bracket of x and y, and z3 of x comma y, the commutator, is equal to 1/12 of the bracket of x with the bracket of x and y, plus 1/12 of the bracket of y with the bracket of y and x. With z of, when y is 0, this is x. When x is 0, this is y. And for z, where the first component is also a z of w comma x on comma y. Is z supposed to be a binary function in this context or an element? I don't know. This is equal to z of w on z of x and y. And that is the end of that chapter. There is one more topic to go before we get to the concepts before we started talking about nilpotent and solvable Lie algebras. I kind of really want to start those on their own video, but you know what? Let's start them on our. Should we power through one more topic? Yeah, I think we should. And just so we get a nice clean transition. So this video might be a little over time, but it's for a good cause. Explicit formula here. So we're going to define a map capital Phi from M inside of the free associative algebra to the free Lie algebra as, well, capital Phi of x1 through x sub n is going to be the bracket of x1 with the bracket of x2 with all the way on to the bracket of x minus 1, the bracket of xn. So it's essentially the composition of the adjoints of every element before x of n acting on x of n. And for these xi in the generating set X. Now we're going to define lowercase phi from M to the free Lie algebra of X as being just, it acts on the series in the same way just scaling essentially just scales capital phi down by the number of components. Theorem. Small phi is a retraction of M onto Lx onto Lx. So this is saying that the restriction of phi onto Lx is just the identity on Lx. And proof. We need that capital phi of u, keep in mind lower phi just scales capital phi down by the number of components of u, so this has to be equal to nu when u has n components. We're going to let theta be the map from the free associative algebra of X to the endomorphisms, the algebra of endomorphisms of the free Lie group Lie algebra on X be the algebra homomorphism extending the adjoint function on the free Lie algebra. Now, to keep going, we need a lemma that big phi of u times v is equal to theta of u times big phi of v for all u in the free associative algebra of X and v in our M. And the proof of this lemma, since everything's linear, we prove by induction on u as the product of xi for the number of components in u. If n is just 1, then we get everything automatically. Now suppose n is greater than 1. Then big theta of x1 through xn of v is just theta of x1 on big phi of x2 through xn phi. That's our induction hypothesis, which is equal to theta of x1 theta of x2 through xn of big theta of v. Once again, induction hypothesis, and so theta of x1, that's a homomorphism, through xn of big phi of v. That's your lemma. Back to our proof. We now show capital phi of u is nu for u in ln of x by induction on n. Once again, if n is equal to 1, our base case, so u is just an element of x, and phi u, is just the identity map, essentially, and so that's automatic. So we're going to suppose that n is greater than 1, that's our induction hypothesis. Then we have u as the sum of the brackets of some vi and wi. Enough to prove when u is the bracket of v and w for v in LP of x and w in LQ of x, with p plus q equals n, and both of these are at least 1. My indenting's all over the place, I'm sorry about that. As theta v is the adjoint representation of v, and theta w likewise, and we get that capital phi of the bracket of v and w is, we can expand out the bracket to be vw minus wv, which, by the fact that big phi is a homomorphism and the lemma, this is equal to theta v times big phi of w minus theta of w big phi of v, which is equal to, from our assumption, this is q times theta v of w times w minus p times theta w v, and that's our induction hypothesis, right? We have big theta u is equal to nu for n up to some value, which is now smaller than, which is in our kind of threshold since we're reducing it down. So this is equal to q times the bracket of v and w, because theta v is the adjoint of v, and likewise we get the same thing here, which is equal to q plus p times v and w by antisymmetry, which is just n, because q plus p splits into n, and the bracket of v and w is by assumption u. We can now give the explicit formula for z of x and y is a function equal to the logarithm of e to the x times e to the y. As before, z is the sum from n equals 1 to infinity of zn, with each zn being the component of degree n. Now, there's a lot of equations we gotta write out here, and then we'll be done. Since e to the x times e to the y this is the sum from 0 to infinity of x to the p over p factorial times the sum of x to the q for q factorial, which is equal to the sum equal to 1 plus the sum for p plus q being at least 1 of x to the p y to the q over p factorial q factorial. We have z is equal to the logarithm, by definition, the logarithm of e to the x, e to the y, is equal to the sum from m equals 1 to infinity of -1 m plus 1. This is just plugging in our previous result into the power series representation of log of 1 plus x. Once again, and then this is just our result from before of x to the p, y to the x to the p, y to the q over p factorial, q factorial to the power of m, which gives us that z is equal to, for pi plus qi summing to at least 1, -1 to the m plus 1 over m times x to the p1, y to the q1, all the way through, multiplied all the way through x to the pm, y to the qm, over p1 factorial, q1 factorial, multiplied all the way through to pm factorial, qm factorial. Now applying our previous capital theta to the monomials, we get that capital theta of x to the p1, y to the q1, multiplied all the way through to x to the pm, y to the qm, is equal to the composition of the adjoints of x to the p1 times and y to the q1 times through to the adjoint of x to the pm times. Now, the last one, if we recall, everything acts on the very last element in the product. So we're actually going to split off 1y from this last term. This whole big series of adjoints acts on y. This is if qm is greater than or equal to 1, and if not, then all of this is the same up until adjoint of x, and this one gets split off. You split one off, and this acts on x. Now, we get this is 0 if qm is at least 2, or if qm is 0 and pm is at least 2. Let me write that better. Hence, the only contributions are from qm equals 1 and for when pm equals 1, qm equals 0. Then, from z to the n being equal to small phi of z to the n, we get the explicit Campbell Hausdorff formula of z to the n equal to 1 over n times the sum of p and q equal to n of z p comma q prime plus z p comma q double prime. Now what are these two things here? We get, oh man, z p comma q prime is the sum for some components p1 through pm adding up equal to p, q1 through qm minus 1 adding up equal to q minus 1, where each pi plus qi is at least 1 and our last pm is at least 1. You know it's going to be good when the summand looks like this and we haven't even gotten to the term inside the sum yet. Of -1 to the m plus 1 over m times the composition of the adjoints xp1 adjoint of y to the q1 through to the adjoint x to the pm acting on y over the factorial of p1, factorial of q1, all the way through to the factorial of pm. And we get that z p comma q double prime is equal to the sum where p1 is as q was before. Sum of p1 through pm minus 1 is p minus 1. Sum of q1 through q to the m minus 1 is q, and pi plus qi is at least 1 of, once again, -1 to the m plus 1 over m of the composition of the adjoints, the adjoint of x, p1 times the adjoint of y, q1 times, all the way through to the adjoint of y, q to the m minus 1 times, acting on x, over p1 factorial, q1 factorial multiplied all the way through to q to the m minus 1 factorial, and we are done. Bit of a longer section here, but now we can get to what I believe probably is going to be the most important topic, the nilpotent and solvable Lie algebras. We've done as much lead up to it as we can possibly do. We are as ready as we are ever going to be. And so I gotta plan out, every book that covers Lie algebras, of course, covers these nilpotent and solvable Lie algebras because they're so important. So I gotta figure out exactly how I'm going to composite all of these discussions into one approach. So look forward to me doing that. Maybe we might recover it sometimes. I don't know how this is going to go.